Hi, this is Miss R, and we're going to talk about the Heat Transfer Lab 5.10. Let's review a little bit before we get going. Let's talk about forms of energy. We've been talking about mechanical, electrical, heat, light, chemical, nuclear, and sound energy. What we're going to focus on today is heat energy, the transfer of that heat energy from one object to the other. Remember, energy changes, but it's never created or destroys. It just changes forms. When we add energy, heat energy, to a solid, it turns to a liquid and then to a gas. So as we add heat energy, those molecules start moving more quickly. And so in a gas, the molecules are moving the fastest. Here's a different picture. This is a solid. This particular solid is ice. Those molecules are locked together and they're moving, but not so much energy. With a little bit more energy, they turn into a liquid and they're not quite as organized, but they're still close together. And then as we add even more heat energy, they spread out to a gas. When the kinetic energy of a substance changes by adding heat, it can change its phase. We just talked about that. When you go from a liquid to a gas, it's called evaporation. You do that when you boil water. You can see all of the steam on top of the water, and that liquid water in the pan is turning into water vapor, a gas. It takes energy from maybe the stove that you've got your boiling water sitting on. If we take the average kinetic energy, which you might do with a thermometer, that's called temperature. And as we add more and more kinetic energy, the substance will go from a solid to a liquid to a gas. So it takes the most energy to go from a liquid here to a gas. That's where you have to add the most energy per gram of substance to get to change the phase. It's the toughest, most energetic phase change from liquid to gas. So when we talk about when we transfer heat from one object to another, there are some different ways we can do that. One of them is called conduction, and that's transfer of heat by molecules colliding with other molecules. For example, if I pick up a scissors, I conduct heat from my hand into the scissors. And the molecules in the scissors and my hand are colliding with each other. And here there's a thermograph here. That's a heat picture. Thermo means heat, graph means picture. The snake is touching a human hand, so the heat from the hand is going into the snake. And we can tell that because the snake is cooler. Here's the temperature scale right here. Dark purple means pretty cool, and yellow means pretty warm. So conduction, touching, is one way to transfer heat. Radiation is another way. You don't touch the sun, but you can still feel the heat of the sun. Radiation does not require matter to travel through. So we absorb heat from the sun or maybe a toasty warm fire with no matter in between the heat source and us. The energy travels versus electromagnetic waves. Here's an example of radiation here in Minnesota. I took this picture on a sunny March day. In the morning, I put out 2 marbles, one black and one white. And we all know that black things in the sun absorb more radiant energy. And so here's the picture a little bit later in the day. You can't see the black marble anymore, and the white marble's still right there. The black marble absorbed a lot more radiant energy from the sun. Even though they were both sitting on pretty cold snow, the black marble sank down because it absorbed a lot more radiant energy and got much warmer. Convection is the other method of heat transfer we're going to talk about. That's by the movement of matter. So some sort of fluid is circulating. This is what happens in your pan of water when you put it on the stove. It's what happens in the mantle of the earth as the magma is conducted around. It's heated and cooled and kind of circulates. It's what happens in your house as warm air rises from your radiator or from whatever heat source you have and travels around your house and then cools as it gets up near the ceiling or gets towards the roof where maybe you have some snow like we do here in Minnesota. Convection is what drives thunderstorms. Warm air rises over maybe a warm field or just the surface of the earth in the summer, or you can kind of feel the convection in a parking lot, the warm air just kind of flowing up if it's a very warm summer day. And then as warm air rises and gets towards the top of the atmosphere, it cools and you get circulation going on. Convection also is responsible for cooling in fins like this. You might have an air-cooled engine in something that you own, and convection cools those fins and cools the engine. So let's see if you remember heat transfer. If the cat is touching the floor, heat transfer by touching, when two objects, their molecules, can collide with each other, that's conduction. If you give someone a hug, you're touching them, so that's conduction. If there's a thunderstorm, heat is rising and circulating and matter is circulating, matter is moving, that's convection. You might have a convection oven that moves hot air around. It's moving matter, so that's conduction. If you stand back from a fire, you can still feel the heat, even though there might not be any warm air blowing on you, and that's radiation as well. And we know that if it's the sun, you're probably getting radiant heat because there's not much matter for that heat to travel through in space. When we use things that don't conduct heat very well, they're called insulation. So you put insulation on your roof and your walls. They're kind of bluish here, and you can see that your windows, even though you might have 2 panes of glass, they conduct heat pretty well, so they're much warmer in this thermograph. If you want to slow down heat transfer, especially to stay snugly warm at night, you tend to use fluffy things that have lots of air in them, like your down comforter or your warm fluffy comforter has a lot of air, and air is not a good conductor of heat. If it's just held next to your body, it doesn't have a lot of density. So if it's just standing still next to your body and you have this nice fluffy thing around you like a pillow, it will hold the heat in and it will not conduct it very well, and it will keep you warm. So things that are poor conductors are good insulators. If you want to slow down heat transfer, use something that's a poor conductor of heat. Insulators, the best insulator is literally nothing. When you use a thermos bottle, some older folks might call it a vacuum bottle, and the reason they call it a vacuum bottle is that inside that thermos there are 2 layers, and they suck out all of the air, so there's very little matter between the inside of the thermos and the outside of the thermos, and if there's nothing there to conduct the heat, it stays warm for a long time. Or if you put something cold, heat can't get in. So now that we know some things about heat transfer, let's go to the lab. Here I've opened up Unit 5 and I've clicked on 510. I've clicked through to the 4th slide here, 4 of 5, and then I'm going to click on the heat transfer virtual lab. In this lab, we're going to use different materials and see if they're better conductors of heat or they're good insulators. So we're going to pick up the tongs. We'll start with glass, put it on the hot plate. We'll grab an ice cube here, put that on the hot plate, turn on the hot plate, and then turn on the timer. And we're going to see how long it takes for the ice cube to melt. This is seconds here, and this is hundredths of a second. So we're watching how well the glass conducts the heat from the hot plate to the ice cube. And the ice, there it goes. It's all gone. So for the glass, our time is 1885. And I'll show you where to write that down, and how to fill out part of the lab sheet. So here's the lab sheet you'll find in doc sharing. There isn't one in the lesson. So look in doc sharing, it does have the direct link to the lab there. So the goal of the lab is to find out which materials are good conductors and which are good insulators, aka really bad conductors of heat. If something's a bad conductor, it's a good insulator. So we want heat to transfer to the ice cube. The heat has to transfer from the glass or whatever other material we're using to the ice to melt it. Remember, the ice cube is absorbing the heat. The heat is going into the ice cube and adding kinetic energy to that solid matter to make it into a liquid. The type of heat transfer we're doing in this lab is conduction. The ice cube is touching. The molecules can crash into each other just like I can grab a scissors or a glass of water, and the molecules can collide with each other. So things are touching. That is conduction. So let's put in our time for the glass. Here we are back in the lab, and for the glass, it took 18 seconds and 85/100ths of a second for the ice cube to melt. So let's go put that in our lab sheet, 1885. So for glass, I'm going to put in 18.85, and I'm going to put seconds here. Some of the materials are going to not be conductors. They're not going to conduct heat as well as glass. It's going to take a long time, and it might take a couple of minutes for the ice cube to melt. So it's important that you write down whether you're writing down seconds or you're writing minutes, seconds, and hundredths of a second. So we'll go back to the lab and start aluminum. So I want to press reset here, make sure my clock is reset, grab the tongs, put away the glass. I want to pick up the aluminum here because that's what we're going to do next. I'm going to grab an ice cube. Make sure you remember to turn on the hot plate. Oh, I think I just turned it off. Now start, and there you go. You're going to have to watch for a while for this ice cube to melt, and I'm going to let you do that on your own. But you know how to set it up. Go to the lab, make sure you use the tongs to pick up a material, put it on the hot plate, turn on the hot plate, then turn on the timer. And don't forget your ice cube. When you finish doing the lab and you filled in all your times here, you can look at the data and then you can answer question 5. We want to know which material slowed the heat transfer the most, which one was the best insulator, and which one was the best conductor. So the one that took the most time is the best insulator because it kept heat from being transferred. It got in the way. Like a nice warm sweater or blankie is a good insulator because it keeps the heat in my body and it doesn't let the heat go out to the environment. So insulators take a long time for the ice cube to melt because they're not good at transferring heat. The best conductor took the shortest amount of time, the least time, and use your data here to support your conclusion here. And that's all you really need to know to get this lab done. Thanks for watching. Here's just one more cool thermograph. Remember, thermograph is a heat picture. Horses can't tell you where it hurts, but I bet if you look at this picture, you can tell which hoof has the injury. Because injuries in your body mean more blood flow to that area, and there's more heat if there's more blood flow. So use your best guess. Thanks for watching. Have a great day.